Okay, today we will discuss uh, Euler Lagrange equation. And then we will discuss symmetries and conservation law and Neuer theorem. So, Euler Lagrange equation and Neuer theorem. So, just like in mechanics, you start with the action, which is integration of the Lagrangian with respect to time, but the Lagrangian L here is taken to be integration of something which is called as the Lagrangian density over the entire space. Here this curly L is known as the Lagrangian density. L of phi del mu phi is known as the Lagrangian density, and it is a functional of the field phi and its derivative. The field phi here in this case depends on what system we are describing. For example, if we consider a system of electromagnetic fields, then the field phi is the gauge field A mu, which is nothing but the vector potential A and the scalar potential there, which is also denoted as phi. If you consider, let us say, electromagnetic field interacting with a pion or some other complex scalar field, then in this case the field in question is a complex scalar field phi, its complex conjugate phi star, and the electromagnetic field A mu. If you consider electron interacting or electron interacting with electromagnetic field, then the field in this question is A mu and psi, which represents the field for an electron. So, depending on the system, we have the field phi and its derivative del mu phi. In general, the Lagrangian density can contain finite number of derivatives. However, most of the system that we study in physics involve only one derivative of the field here. So, I will consider the Lagrangian density to be a functional of the field phi and all its first derivative del mu phi. Here I should explain what this notation means. The spatial coordinate I take them to be x mu to be x and t, where x denotes the spatial variables and t is the time. X 0 is represented as t and xi's are the I components of this x. So, this index mu here runs 0, 1, 2, 3, 4 variables. So, we will take this action. From this we can see that the action S is actually d4x times the Lagrangian density phi and del mu phi. We will vary this action S by keeping the fields variation of the field delta phi equal to 0 at the boundary, and this will give me the field equations. So, let us do that. So, delta S, by setting delta S to be 0, is equal to integration over d4x del L over del phi delta phi plus del L over del of del mu phi delta of del mu phi. At any given point, delta of phi is basically phi prime of x minus phi of x. So, as you can see, the variation does not depend on space time point. So, therefore, delta and del mu can commute. So, I can write delta of del mu phi as del mu of delta phi. I will substitute this here and then I will do some rearrangement. So, that will give me delta of s equal to integration d4x del L over del phi delta phi plus del L over del of del mu phi del mu of delta phi. Now, what I will do is I will take the second term and then I will write it as a total derivative minus some quantity. As you can see, the second term can be written as del mu of del L over del mu phi times delta phi minus del mu of del L over del mu phi times delta phi. I will substitute this here, and when I substitute, what I get is delta s is equal to integration d4x. I will collect the terms which come with a factor of delta phi together, and then I will write it as delta phi times del L over del phi, and this term here minus del mu of del L over del mu phi. Then I have this term plus del mu of del L over del mu phi times delta phi. Now, you can see the second term is a total derivative. So, we can use Gauss divergence theorem and then we will get an integration at the boundary. However, we require that the variation of the field at the boundary vanishes. So, therefore, the contribution of this total derivative term is 0, and hence the variation of action actually depends on some term which is multiplied by delta phi. Delta phi is arbitrary infinitesimal variation, and hence delta s will be 0 if and only if the quantity here in the bracket is 0. Hence, by varying the action, we got the Euler Lagrange equation, which is this quantity inside the bracket equal to 0. So, the Euler Lagrange equation of motion is given by del L over del phi minus del mu del L over del mu phi is equal to 0. Now, we also need to introduce conjugate momentum and Hamiltonian in order to quantize. We will quantize the canonical way, just the way you quantize in non-relativistic quantum mechanics. You consider the coordinate variable and then you consider the corresponding conjugate momentum. You start with the canonical commutation relations and quantize the theory. We will do exactly the same way, and hence we need to introduce the conjugate momentum corresponding to the field phi. So, the conjugate in this case what we will have is the momentum density. So, conjugate momentum density pi of x equal to del L over del of phi dot. Then the Hamiltonian density h of x is defined to be pi note that phi dot here the dot represents derivative with respect to time minus L of phi del mu phi. The Hamiltonian density is defined to be this. Now, what we will do is we will discuss the Neuer theorem in somewhat detail. So, Neuer theorem states that for every continuous symmetry, there is a corresponding conserved quantity. We will explain what, when do we call a quantity to be conserved as we go on. So, let us start with the Neuer's theorem. So, the statement is that continuous symmetry implies conservation law. When do we say that we have a symmetry in the theory? You consider the field phi of x. Suppose you make a transformation, the field goes to some transformed field phi prime of x prime. If the equation of motion has the same form, if the form of the equation of motion does not change, then you say that this transformation of the field phi of x to phi prime of x prime is actually a symmetry of the theory. So, form of the equation of motion remains invariant. Implies you have a symmetry. This will happen if the action when S remains invariant. Under this transformation. So, you make this transformation, and then if the action does not change under this transformation, then classically you have a symmetry in the theory. in this case what we will discuss is we will discuss continuous symmetries. The symmetry transformations, the set of symmetry transformations which are actually parameterized by continuous parameters. These are known as the continuous symmetries. So, what we will see what happens when the system remains invariant under a continuous symmetry. Neuer's theorem states that continuous symmetry implies certain quantity remains conserved, and this is what we will see in the subsequent discussion. So, what kind of symmetry transformations that we come across in physics? Mostly we will discuss relativistic quantum field theory. So, we keep seeing Lorentz transformation, where the space time coordinates actually change like x mu going to lambda mu nu x nu. This is also known as the homogeneous Lorentz transformation. We have inhomogeneous Lorentz transformation or Poincare transformation, which is this Lorentz transformation plus a translation. So, x mu under Poincare transformation goes to lambda mu nu x nu plus some translation a mu. Also, in electrodynamics you see there are these vector potential A and scalar potential phi, and if you make the transformation such that A goes to A prime, which is A plus gradient of some scalar which I will call as alpha, and if phi goes to phi prime, which is phi plus del alpha over del t. I am not sure about the minus sign, I think this is a minus sign here. Then the electric and magnetic field E and B remains invariant. Unlike this transformation does not depend on the space time parameter. So, this happens at the same point, at the same spatial point at same time. So, x and t. So, this is known as the gauge transformation. In 4 vector notation I can write it as a mu, the 4 vector a mu under this transformation goes to, strictly speaking, a mu of x goes to a mu prime of x, which is a mu of x plus del mu of alpha. Plus del mu alpha. So, this happens at the same point in this space time. This is an internal symmetry transformation. So, you have Poincare transformation and you also have internal symmetry. Under this transformation also the equations of motion in electrodynamics remains invariant. So, there are such transformations. We will discuss what happens under such transformations. Under internal symmetry transformation, phi of x, the field phi of x goes to phi prime of x, which is equal to phi of x plus some delta phi. If I consider infinitesimal transformation, then this is what I get. More generally, the field phi of x will transform to some phi prime of x prime, where both the field as well as the arguments change under this transformation. So, this will be a combination of some internal symmetry transformation as well as the Poincare transformation. What we will do is that we will first consider this simpler case and then we will see how do we get conservation laws under such a transformation, then we will discuss about the second possibility, which is much more general than this one. So, let us consider the variation here. Strictly speaking, we should require the action to be invariant under such transformation. What we will do is that we will restrict ourselves to the special case where the Lagrangian density remains invariant under such transformation. If the Lagrangian density remains invariant, then obviously the action is invariant. However, the Lagrangian density can actually change up to some total derivative, and if the fields vanish sufficiently fast at infinity, then also the action will remain invariant. We will not worry about the second possibility here. So, we will consider the case where the Lagrangian density L remains invariant under such transformations. So, delta L is 0 under such transformation. What is delta L? Delta L is nothing but del L over del phi times delta phi plus del L over del of del mu phi delta of del mu phi. We will consider the field configurations which obey the classical field equation, the Euler Lagrange equation. Remember here this variation is done at every point in the space time, okay? And we will consider the field configurations which satisfy the Euler Lagrange equation. So, we will use the Euler Lagrange equation to substitute for the first term here. Using Euler Lagrange equation, we find that del L over del phi is equal to del mu of del L over del mu phi. So, this we will substitute in the expression for delta L to get delta L equal to del mu of del L of del mu phi delta phi plus del mu of del L over del mu phi times del mu of delta phi. As you can see, again I have exchanged delta and del mu because this delta transformation here does not depend on x, on the space time points x mu. Now, you can see if you combine both these terms, you will get a total derivative. So, this quantity is nothing but del mu of del L over del mu phi times delta phi. This is of the form del mu j mu, where this 4 vector j mu is equal to del L over del mu phi times delta phi. So, the invariance of the Lagrangian means that delta L equal to 0. So, if delta L equal to 0, then del mu j mu equal to 0, where j mu is the quantity given by this expression. Whenever this happens, you call this quantity j mu to be a conserved current. So, del mu j mu equal to 0 implies j mu is a conserved current. So, what we have seen is that if we require the system to be invariant under a continuous internal symmetry transformation, then we find an equation, we get an equation like this, provided the field configuration obeys the equations of motion, and hence we get a quantity, we get a 4 vector which remains conserved. What do we mean by some quantity which remains conserved? We will see it in a moment. So, let us write this equation in terms of components. What we get is del j mu over del t plus del j 0 over del t plus del dot j is equal to 0. Now, I will integrate it over the entire space, and I define some quantity which I will call as q of t. Q of t is defined to be integration of j 0 of x t over the entire space d cubed x. Then this implies dq of over dt is equal to minus integration of, I think there is a minus sign here. So, this will be integration of d cube x del dot j, and if I use Gauss divergence theorem, what I will get is integration of j dot ds at the boundary, and if the outgoing flux vanishes or if the fields go to 0 sufficiently fast at infinity, then this quantity equal to 0. Therefore, the rate of change of this quantity q of t actually is equal to 0. So, this implies dq over dt equal to 0. So, this quantity here which I defined to be q remains constant in time. So, what we get is a quantity which remains conserved.
That should be a plus sign because dq/dt is minus j dot ds.
So, what I get is del 0 j 0 plus del I j I equal to 0, right? And I am using a metric which is eta 0 0 equal to 1, eta I j equal to minus delta I j, and del dot j in the usual sense is just del I j I, right? So, that will give you a minus sign. When this becomes a covariant j, I will acquire a minus sign, and here therefore, I will have a minus sign. So, what we see is that the rate of change of the charge is actually 0, provided the fields vanish sufficiently fast at infinity. So, a continuous symmetry implies a conservation law. This is what we have seen. We can see a very simple system, and then we can construct the charge for this system. So, let us consider a system of a complex scalar field. Phi and its complex conjugate phi star of x are linearly independent, and let us consider the Lagrangian to be Lagrangian density L of phi del mu phi to be half, I think no half is there, del mu phi star del mu phi minus some potential v of phi star phi. This Lagrangian density is invariant under a continuous global transformation, that is, if phi goes to e to the power I alpha times phi, and hence phi star goes to e to the power minus I alpha times phi star. Under such a transformation, phi star phi remains invariant, therefore, the potential term here remains invariant, and in the kinetic term also you get a e to the power minus I alpha here from the first term and e to the power plus I alpha from the second term, because alpha is a constant, it does not depend on space time variables, and hence the first term also remains invariant. So, such a system is invariant under a continuous global symmetry. We will see what is the corresponding conserved current for such a system. We will consider the infinitesimal form for this transformation. So, if I consider infinitesimal transformation, then phi goes to phi plus delta phi, where delta phi is I alpha times phi, and phi star here goes to phi star plus delta phi star, which is where phi star is minus I alpha phi star, delta phi star is minus I alpha times phi star. So, we will substitute this in our expression for the conserved current J mu, which is given by del L over del mu phi times delta phi. In this case, we have two independent fields phi and phi star. So, whenever there are more than one field, we have to sum over the fields here. So, in this simple system, the conserved current is actually this plus del L over del mu phi star delta phi star. If there are more than two fields, then you have to sum over all such fields. From the Lagrangian density, you can derive what is del L over del mu phi. Del L over del mu phi is nothing but del mu phi star, and del L over del mu phi star is del mu phi. So, I will substitute this and also the expression for delta phi. Then what I see is the J mu is equal to I alpha times phi del mu phi star minus phi star del mu phi. So, for this very simple system, the conserved current have this expression, it has this expression, and the corresponding charge q of t, which is integration d cube x j 0 of x t, is given by I alpha integration d cube x phi del 0 phi star minus phi star del 0 phi. All right. So, this is the quantity which remains conserved as a continuous of as a consequence of the continuous global symmetry. Now, in the remaining part of this lecture, we will consider the more general scenario. That is when the field, when the argument of the field also changes. So, phi of x goes to phi prime of x prime. Phi prime of, we will introduce some variation which I will call as delta tilde of phi, which I will define to be phi prime of x prime minus phi of x, in order to distinguish this from the variation delta of phi which I have introduced earlier, which is phi prime of x minus phi of x. We need to keep in mind that in this case we have to require the action to be invariant. It is not sufficient to consider the invariance of the Lagrangian only is the argument of the fields also get transformed. Let us rewrite this variation delta tilde of phi in a way which we will need for later purpose. So, delta tilde of phi can be written as phi prime of x prime minus phi prime of minus phi of x prime plus phi of x prime minus phi of x. So, what I did is I have added phi of x prime and also I have subtracted the same thing. So, this so I just write it in a rewrite it in a trivial way. However, now you can see that this quantity here is nothing but delta phi of x prime. The first two terms give me delta phi of x prime and the last two terms give me, for infinitesimal transformation, this is nothing but del phi over del x mu delta x mu, right. So, delta tilde of phi is given by this, but if I keep the transformation to first order invariations, then I can rewrite this here as delta phi of x plus del phi over del x mu delta x mu, because these two terms here will differ by second order quantities. So, what I get here is delta tilde phi is equal to delta phi plus del phi over del x mu delta x mu. Lecture we will consider the invariance of the action under this transformation and find the corresponding conserved quantities. Okay, thank you.